Hi everyone, my name's Nate. I'm going to build on the idea of the last video where we talked about the force between two charges. All we talked about was the magnitude, how much force is between it. We didn't necessarily consider what direction the force is acting in, which is very, very important. For instance, let's consider two charges. If I tell you both are a positive charge, alright? Cool, well, they're going to push apart. We know that much. If we say this is Q1 and let this be Q2, if I were to ask you, how would the Q1, what kind of force would Q1 put on Q2? Not necessarily concerned with how Q2 is affecting Q1, but how Q1 affects Q2. That's going to push it away. In which case it's going to have a force acting in that direction. In that case, this is going to be our force 1 on 2. Important to note, I did draw an arrow above it to show it is in fact a vector. Reason being, it has a particular direction it's acting upon, and of course a magnitude that we went over last video. Although if I were to tell you instead you had a charge here and a charge here, but unlike the previous example, if that was a negative charge and this was a positive charge, yeah, I'm still letting this be Q1 and this be Q2. It would pull it in, as opposed to pushing, it would pull. So the force Q1 has on Q2 it's going to pull it in. Now, important to note, if these guys are the same value, just opposing signs, for instance, if this is 5 nanocoulombs and this is negative 5 nanocoulombs, I mean that force is going to be the same magnitude but opposite direction. Now, to give a bit of a more formal, I guess you'd say, explanation to this, let us consider we have an origin point. Alright, that's going to be our frame of reference, lack of the better word. It's going to be our origin. Now, in this system that we're considering, we have two charges that are located some distance from the origin, and some distance from each other. So, consider this just arbitrary points. Let this be Q1. I'm going to put our Q2 down here. Alright, Q1 has some distance from Q2, although it also has some distance from the origin. Q2 also has some distance from the origin. Where this becomes important, the idea of using the vectors as opposed to just the magnitudes. If I were to ask you, well, what's the distance from origin to Q1? Well, you'd say, oh, well, you know, just measure this guy out here. Actually, I guess for the sake of being neat, let me use this guy. Once again, this guy's awesome. Don't know what I would do without him. So, you just measure these out and tell me, oh, well, you know, this is so many centimeters and this is so many centimeters. If I drew this accordingly to where this was, say, 15 centimeters long, and this was also 15 centimeters long, well, if I were to ask you, okay, how far is Q1 from the origin, that would be right. But if I were to ask you what direction is it pointing in, that's not very descriptive. I don't know if you're talking about this or this or. The vector has both magnitude and direction, meaning we're going to have some magnitude against some unit vector. Now we already know the magnitude between origin and Q1 is going to be some distance r. So let's go ahead and say this entire thing colors, where's colors, things, colors. This entire distance from the origin to Q1, we're just going to let it have value little r1. Same thing for origin to Q2. Has magnitude R2. Now, we're going to define our unit vectors for this magnitude to be, I guess I don't really need for it just to be a unit vector. Short. To be pointing in that direction, which that'll be accordingly your a hat 1. And this will be your a hat 2. In which case, of course, your actual vector from origin to Q1 will be R1 times your a hat 1. Is that the right? Yeah. In which case, I guess, let me go ahead and write this up here, just to be explicit about it. R1 is equal to the actual magnitude times unit vector in that direction. R2 is equal to the magnitude of R2 multiplied by some distance, some direction, A2, which is exactly what we defined here. Now, if you'll recall from Calculus 3, suppose you have, I'm going to go up here real quick. Just start, oh no, all over the, well, that's something added to the clipboard, I guess. If you insist. If we have, consider a vector, that direction, a vector in that direction. We're going to find this vector here is vector A, and this vector is vector B. Of course, vector A is pointing in that direction, B is pointing in that direction. Now, if you want to consider this distance between the two, from the tip of A to the tip of B, that would be B minus your A vector. Similarly, if the whole point of showing this to you is that we're wanting to find an expression for how Q1 is affecting Q2. So we're going to state our R vector as pointing in the direction of Q2. Simple enough. Meaning, if Q1 and Q2 are both positive forces or negative, 2 positive makes a negative. If we define our R in this direction, that means that the force that Q1 is acting on Q2, it will be pointing in that direction, which would be right. It would push it away from Q1. And if Q2 is actually negative, positive times negative is a negative, it's going to be pointing in that direction, which means it pulls. Exactly how we described it earlier. Now, same way I did for this guy right here, I'm going to reapply that idea between R2 and R1, in which the actual vector pointing from Q1 to Q2 is R2 minus R1. Hope I'm not skipping any steps. I'd rather go too in-depth than not as in-depth. They're called steps for a reason. They're not gaps or leaps. I don't expect you to have climbing gear or the ability to scale high heights. I'll build the tiny steps for you to walk from point A to point B. That's important to me. We'll actually show this as R12, which is what we want to be acting in the direction of F12, in which our R12 will be equal to R2 and R1. For this vector, R12, there is, of course, the actual magnitude, and we're acting this in a particular direction, A hat 1, 2. So, we can write the force Alright, a little bit of explanation. Wrote it down. What this is saying, product of Q1, Q2 in the direction of A12. All of that, of course, divided by our constant 4 pi epsilon naught and the square of this distance. So, this is how you would generally, let's say that, generally write out Coulomb's law. The next video, I'll go over some different formulations of this that are actually extremely useful. Straight lines. But ultimately this expression is what I was trying to get across in this video. This diagram. Hope that made sense. Let me know what you think. Hope you enjoyed the video. Thanks for watching, definitely. And I'll see you in the next video.